All right, so we're going to finish up our discussion in Chapter 5 with a discussion about graphs of polar equations. So in the last section we talked about polar coordinates, and we graphed a couple of equations just by plotting some points, but I want to change our perspective a little bit in 5.7 and maybe sort of develop our intuition a little bit in terms of what kinds of graphs we can expect from what kinds of equations. So whenever you have an equation of the form r equals a plus or minus b cosine theta or a plus or minus b sine theta, then you're going to get a graph that's, we call these things limacons, and there are different kinds. So some of them just look practically like circles, but with like a little bit of a flat side. Some of them have a little bit of a dimple. Some of them have a straight up cusp like this one, and we call these ones cardioids because they look like hearts, kind of. And then some of them have an inner loop. And the way that you can decide which kind of graph you're going to get is by comparing these coefficients, a and b. So if a divided by b is less than 1, then you're going to get an inner loop. So if you had something like 2 plus or minus 3 cosine theta, right, then a over b would be 2/3, right, less than 1, and so you would get an inner loop. If the coefficients are the same, right, so if a over b equals 1, right, so if a and b are the same number, then you're going to get the cardioid. If a divided by b is between 1 and 2, then you get this little dimple. And then if a over b is greater than or equal to 2, then you just get kind of like a flattened edge without a dimple in it. The other thing that I'll say about these limacons is that some of them kind of bulge out to the right or to the left, and some of them kind of bulge up and down. So all of the limacons you're seeing here are they're all bulging out to the right, I guess you would say. Those are all cosine, right? So those are all versions of like the top equation. If it was a plus or minus b sine theta, then this whole thing would be rotated 90 degrees, and so the little dimple would be pointing up, I guess, or the inner loop would be pointing up, and the whole graph would be pointing sort of more in the upwards direction. In fact, that's what happens when you have, so this is what happens when you have a plus b cosine theta. If you had a minus b cosine theta, then this whole thing would be flipped over, right? These would all be flipped over the other direction. And again, for sine, they would be rotated 90 degrees if it was a plus b sine theta. If it was a minus b sine theta, it would be rotated 90 degrees in the other direction. So you can kind of get some intuition, right, looking at these things. And a good thing to do, possibly, if you're trying to get a little bit more intuition, would be to go to Desmos and just plot a bunch of these things in Desmos, right? Just play around with the values of a and b and stuff, and see what different kinds of graphs you get. So that's one common type of polar graph that we will see. Another common type of polar graph would be something that has the form r equals a cosine n theta or r equals a sine n theta. We call these Rose curves. And Rose curves are kind of interesting. If n is an odd number, then that's the number of petals that you're going to have on your rose. So for example, this would be a cosine 3 theta. So 3 theta, so you have 3 petals. And the petals are equally spaced around your axis system. So, and this one is a sine 5 theta. So again, 5 theta, so you have 5 petals. So if n is odd, then n is the number of petals that you're going to have. But if n is even, then you have 2n petals. So for example, right, so here's sine 2 theta. So you have 2 times 2 is 4, so you have 4 petals, right? And here's cosine 4 theta, so you have 8 petals, right? 2 times 4 is 8, so you have 8 petals. So again, if n is odd, then you have n petals. If n is even, then you have 2n petals, which is kind of interesting. And then the length of each petal is equal to a, so it's equal to this number that you're multiplying on the outside of the function, right? And then finally, if you're talking about like what's the difference between the cosine and the sine version of these things, Well, if it's a cosine, then the first petal is going to open up right on the polar axis. Okay? Whereas if it's sine, then the first petal opens up kind of oblique to the polar axis, so it's not going to open up right on the x-axis. Okay, but with cosine, the first petal always opens up right on the x-axis. With sine, it opens up, somewhere oblique to it. If you're trying to figure out where that first petal is, in the case of cosine, it's going to happen at 0, right? But in the case of sine, if you're trying to figure out, well, where does that happen, then you should figure out when sine of n theta is going to equal 1, because that's the largest that sine can ever get, right? So you should figure out for what value of n times theta is sine of that angle going to equal 1, and that'll tell you where your first petal opens. So those are rose curves. Then we have circles and lemniscates. So circles have the form a cosine theta or a sine theta. Or another way you can get a circle is if you just had like r equals a. So the curve r equals a is just a circle centered at 0, 0 with radius a. But if you have a circle that's not centered at 0, 0, then it's going to be something like this. Although these circles that have this format, they always have one of their edges on the point 0, 0. But anyway, r equals a cosine theta is going to open up to the right. R equals a sine theta is going to open up along the kind of y-axis, I guess you could say. And then lemniscates are when you have r squared equals a squared sine 2 theta in this case, and r squared equals a squared cosine 2 theta. So those are circles and lemniscates, and then you have spirals. We graphed a spiral yesterday. So yesterday we graphed the spiral of Archimedes, which looks kind of like this. This is just the positive half of the spiral. The negative half would be kind of going in the opposite direction, as we saw in 5.6. But there are other kinds of spirals as well. With these things, I think the best thing to do is just to plot some points to see what's going on. But generally speaking, you're going to get these spiral things whenever you have, r is some function of theta, but it's not a trig function. It's not a trig function of theta. Okay. Let's practice. So let's practice graphing some of these things. Okay, so this first one, r equals 4 sine 3 theta. I can tell by the format of this equation that this is going to be a rose curve. I know it's a rose curve. I know it's going to have 3 petals. I know that the length of those petals is going to be 4, right? 4 units. And then I know that if it were a cosine 3 theta, the first petal would open up right on the x-axis. But this is a sine 3 theta, so I'm expecting the first petal to open up somewhere else. Now, if I want to figure out where the first petal opens up, well, then I could say, I know that sine is going to be 1 whenever we're at 90 degrees. So when is 3 theta equal to 90 degrees? Or in other words, when is 3 theta equal to pi over 2 radians, right? So we could say, when is 3 theta equal to pi over 2 radians? Well, that happens when theta equals pi over 6, right? If you divide both sides by 3, you get theta equals pi over 6. That tells you that that's where your first petal is going to be. It's going to be at the angle of pi over 6. And the length of that petal is 4. 1, 2, 3, 4. So there's my first petal. And then there are 3 petals, but they open up evenly. So they're evenly spaced, I guess you could say, around 2 pi units. So if you divide 2 pi by 3, you get, of course, 2 pi over 3. So the next petal is going to be 2 pi over 3 units away from this one. Okay? Oh, that's kind of hard. 2 pi over 3 is well, so 2 pi over 3, this would be another pi over 6. This would be pi over 3. And this would be 2 pi over 3. So I think at 2 pi over 3, I'm going to be here. 1, 2, 3, 4. and then 2 pi over 3. Let's see, there's pi over 6, that's pi over 3, and then another pi over 3. So there's two. So another 2 pi over 3 units would put me there. Now you're welcome to verify this, right? So in other words, I'm claiming that if you plug in, this angle is 5 pi over 6 right here, right? So I'm claiming if you plug in 5 pi over 6 for theta, what do you get? So you get 5 pi over 6. 3 times 5 pi over 6 would be 5 pi over 2, right? Sine of 5 pi over 2 sorry, give me a sec. Sine of 5 pi over 2 is 1, sure enough, right? And 1 times 4 is 4, right? So we've reached our maximum. The same thing if we go all the way out to 3 pi over 2, right? So if I plug in 3 pi over 2, 3 times 3 pi over 2 is really 9 pi over 2, and sine of 9 pi over 2 is equal to 1 as well, right? So sure enough, you end up there. Okay. And then obviously, right, if you plug in like 0, 3 times 0 is 0, and sine 0 is 0, right? So we're going to be passing through the pole after we hit each pedal, I guess you could say. So this is what the graph of the function ends up looking like, right? It's like this rose curve that looks something like this. And it's going to continue to repeat. It's going to trace out the same 3 pedals over and over and over again. You can verify this. I would encourage you to make a table of values like this. Plug in some things for theta and see what you get for r. I don't know why I wrote it backwards, theta and r. But anyway, plug in some things for theta and see what you get for r to kind of verify that your picture is correct. So you're welcome to do that, and I would encourage it. But this is a rough sketch of what this thing is going to look like just based on the format that we have. Okay, so there's a rose curve. Part B is another rose curve. 4 cosine 4 theta. See if you can see if you can get a rough sketch for what this graph would look like. Go ahead and give the video a pause and see if you can do that. Okay, so here's my solution. Another rose curve, like I said. This time n is an even number, so we're going to have twice this many petals. So we're actually going to have 8 petals. Those petals are also going to be 4 units long, right? They're each going to be 4 units long. And I know that the first one's going to open up right on the x-axis because this is a cosine function, right? In other words, when theta is 0, 4 times 0 is 0, and cosine of 0 is 1. So of course you're going to reach your maximum when theta equals 0. 1, 2, 3, 4. And then the other 7 petals are equally spaced around this graph. So if we wanted to figure out where the rest of them are, we could go 30 degrees, 30 degrees, 90 degrees. So we have 1, 2, 3, 4, 5, 6, 7. Oh, that's too many. So they're not. So maybe it's every 45 degrees, right? 1, 2, 3, 4, 5, 6, 7, 8. Yep. So 1, 2. So they're going to be every 45 degrees is where we're going to have a petal. And of course, there are going to be moments when this thing passes through 0, 0 as well. Like when, when would that happen? That would happen when theta is, or when you're taking cosine of pi over 2. So I guess if theta is pi over 8, right? Then 4 times pi over 8 is pi over 2, and cosine pi over 2 is 0, right? So you will pass through this point. That's not the only place it happens, right? It happens over and over and over again. But yeah, so this is a rough sketch of what this thing is going to look like. Oh, I mean, I don't know exactly. I would have to do some more work to figure out like in what direction these things happen. I'm just going to kind of piece it all together like this. This is not the way that the curve actually gets traced out if you make your table of values. But the picture is going to end up looking like this. Let me just show you what I mean. So if I plug in you know, 0, and then pi over 4, and then pi over 2, and then 3 pi over 4, and then pi, 5 pi over 4, 3 pi over 2, and 7 pi over 4. So if I plug in each of these, what do I get? So I'm going to get 4, of course. Well, I'm going to get 4 in each of these places, but some of them might be a negative 4 though, right? So at pi over 4, 4 times pi over 4 would be pi. Cosine of pi is negative 1, right? So at pi over 4, I'm at negative 4, right? So at pi over 4, I'm actually at negative 4. I'm actually at this point here. So what I'm trying to say is I would start at this point, but then I would actually go down to this point is my next place that I would go. So if I was tracing this in order, I would start here, come back there. If I plug in pi over 2, 4 times pi over 2 is 2 pi. Cosine of 2 pi is 0, right? Or sorry, 1. And 4 times 1 is 4. So then I'm back up here. So I start at this point, I work my way down to this point, and then I would come up to this point here. Okay? At pi, if I plug in, that's if I plugged in pi over 2. If I plug in 3 pi over 4, cosine 3 pi, so then I'm at negative 4. So I think this is going to alternate like this, right? Between positive 4 and negative 4. So in other words, at 3 pi over 4, I would actually be down at negative 4 over here. So I start here, I work my way down, then I work my way up here, then I would work my way down here. You see? So the way that they get traced out, like if you're tracing this out in order, is, you know, it goes this way, then this way, then this way, then this way. Then I would assume it probably goes out this way, and then this way, and then this way, and then this way, and then this way, right? And then you end up like back where you started. But that's the idea there. That's the rose curve that you get. Part C. 1 minus 2 cosine theta. This is a limaçon. And if you compare A over B, it's 1/2, right? So note that this is a limaçon. A over B is 1/2, which is less than 1. So that tells you that you have an inner loop, right? So you have an inner loop. Right? That's what we talked about on the first page, right? If A over B is less than 1, then you get an inner loop. Which way is this opening up? It's a 1 minus 2 cosine theta, so I think it's going to be opening up to the left, right? So I'm going to say opens left. It doesn't really open because it's a closed curve. It's a closed curve, but it sort of bulges out to the left, I guess you could say. So it opens left. So this is the information that I have. Now that all by itself maybe doesn't give us a great clue as to what this thing looks like. I think we need to plot some points on this to really get a good picture, but at least we know more or less what to expect here, right? We expect to find this thing opening out to the left and for it to have like an inner loop that takes place. So I'm just going to plug in some values for theta. Since it's opening out to the left, I'm thinking that plugging in pi is going to be very important, but probably plugging in 0 is too. Let's plug in just kind of some standard. We'll plug in 0, pi over 2, pi, 3 pi over 2. And then if we need to come back and fill in some blanks, we will. Okay, but if I plug in 0, cosine 0 is 1, 2 times 1 is 2, 1 minus 2 is negative 1. If I plug in pi over 2, cosine pi over 2 is 0, 2 times 0 is 0, 1 minus 0 is positive 1. If I plug in pi, right, cosine pi is negative 1, negative 2 times negative 1 is positive 2, and 1 plus 2 is 3. And then at 3 pi over 2, cosine is 0 again, so I'm going to be back to 1. So let's just plug in those things, right? So I have 0, negative 1. Then I have pi over 2, 1. Then I have pi 3, 1, 2, 3. And then I have 3 pi over 2, 1. Okay, so this must be the large bulge, and then this must be the inner loop that takes place. Maybe to have a better clue of what this thing looks like, I might want to plug in something like pi over 4. That might be a good one to plug in. Cosine of pi over 4 is root 2 over 2, so 2 times that would just be root 2. And 1 minus root 2 is about negative 0.4. So at pi over 4, I'm at negative 0.4, right about there. 3 pi over 4 might be another good one. So cosine of 3 pi over 4 is negative root 2 over 2. So this is going to be 1 plus root 2. That's like 2.4-ish. So 2.4 when I'm at 3 pi over 4. So I get 2.4. I'm going to get the same thing down here, right? Or sorry, here. Not that point, that point. And then at 7 pi over 4, I would be at negative 0.4 again. Okay. So I think I have some clue of what this thing is looking like. I know that I'm going to get some values over here. So let's think. Well, yeah. Okay. So when theta is 60 degrees, notice that cosine theta is going to be 1/2. 2 times 1/2 is 1, and 1 minus 1 is 0. So at 60 degrees, I'm at 0. I wonder what I'm at 30 degrees. So cosine 30, root 3 over 2, 1 minus root 3. Oh, that's still going to be negative. So that really doesn't help me. Well, I know that in order to be passing through 0 at some point, I have to be positive over here somewhere. But anyway, so I'm starting here at 0, negative 1, and then I go to pi. Then I go to pi over 4, negative 0.4. That was that point right there. And then from there, I'm going from there to 0 at pi over 6. And then by the time at pi over 3. And then by the time I get to pi over 2, I'm up here at 1. So you see I'm tracing out that inner loop, I think. At 3 pi over 2, I'm over here at 2.4. Or sorry, I mean at 3 pi over 4, I'm at 2.4. And then at pi, I'm over here at 3. At 5 pi over 4, I'm back at about 2.4. At 3 pi over 2, I'm back down to 1. At 7 pi over 4, I'm back here at negative 0.4. And then when I get back to 2 pi, I'm going to be at 0 again. Right? So that's the limacon that gets traced out. Okay, so it's useful to have some idea about what this thing looks like before you go to graph it, which is sort of the whole point of this section. Help us build up our intuition. Okay, see if you can do part D on your own. So give this a pause, see if you can figure out what part D is, what it should look like, see if you can graph it. Okay, part D is a cardioid. I mean, it's a limacon, but more specifically, it's a cardioid because A over B equals 1, right? So A and B are the same thing. So this is a cardioid. And since it's a 3 plus 3 sine theta, it's going to bulge up. So in other words, it's going to be like an upside down heart. It's kind of going to look like an upside down heart. So the little cusp is going to end up like down here somewhere. Okay? So it's like an upside down heart, right? More or less. So that tells me, you know, the maximum value is going to happen when sine is equal to 1. That happens here at pi over 2, right? When I plug in pi over 2, I'm going to get sine pi over 2 is 1, 3 times 1 is 3, and 3 plus 3 is 6. So at pi over 2, I'm up here at 6. 1, 2, 3, 4, 5, 6. The minimum value is going to happen when sine is negative 1. Sine is negative 1 at 3 pi over 2. Right? When sine is negative 1, we're going to have 3 minus 3, which is 0. So over here at pi over 2, I'm at 0, right? So that's that cusp, right? So it's going to go kind of like this, right? And then come back out. In fact, I'm pretty confident that I could just graph it at this point. But let me get a couple more points. If I plug in 0, right? Sine of 0 is 0. So this is going to be 1, 2, 3. And same thing at pi. I'm going to get 0, so 1, 2, 3. So, so the curve looks something like this. Oh, it should be a little more symmetric than that. That was a very poor job. But that's basically the idea. If I were to plug in something like pi over 4, right, I'd get root 2 over 2. So I get 3 plus 3 root 2 over 2, which is about 5.1. So at pi over 4, I'm at 5.1. 1, 2, 3, 4, 5.1. So I needed to make it a little fatter, right? It's kind of a fat heart. So I suppose the same thing's going to happen over here, right? So 1, 2, 3, 4, 5.1. So really it should come out a little wider. It should be a little bit wider than what I drew. But anyway, that's kind of the picture you're going to get. Okay, it's just going to trace that thing out over and over and over again. So the wide picture, right? The pulled one is the one that we're looking at. Right, that's what the cardioid looks like. So that's that one. Again, you're welcome to plug in some points to kind of, fill in your picture, make it look a little bit better. But that's kind of the rough sketch that we get from knowing what the picture looks like, from knowing that it's a cardioid. Okay. So those are some common polar graphs. We can also look at the conic sections in polar form. So this kind of ties together what we were talking about at the first half of the chapter with polar equations, which we've been talking about for the last couple of sections, okay? But yeah, there are some common graphs of conic sections as well. So if a conic section has a focus at the pole 0, 0, then it's going to have one of the following forms. Okay, so it doesn't have its center at 0, 0, but one of its but one of its foci is going to be at 0, 0. Okay, so when that happens, the conic section gets one of these forms. Generally speaking, the equation of a conic section in polar form is very complicated and messy, but if we have one of the foci at the pole 0, 0, then it becomes really pretty nice. So it has one of these following forms, and the way that you can tell what kind of conic section it is based on this number e. Right? So it's based on the number e. E is called the eccentricity of the conic section. So e is the eccentricity. If e is less than 1, then the conic section is an ellipse. If e equals 1, then the conic section is a parabola. And if e is greater than 1, then the conic section is a hyperbola. You'll notice that this is really similar to the discriminant idea when we were looking at conic sections earlier. we said if the discriminant, I'm just going to call it D. If the discriminant was less than 0, then we got an ellipse, right? If the discriminant was equal to 0, then we got a parabola. And if the discriminant was greater than 0, then we got a hyperbola. So it's the same notion here. Only instead of 0, only instead of zeros now it's 1. And the way that we make the determination is based on the eccentricity. So here's how this works, right? You have to make sure that the number in your denominator, that this constant term in the denominator, it has to be 1. So, for example, on number 3, and by the way, e is always a positive number, because look, it could be a minus or a plus. So we always take e to be like just the positive version. Anyway, so looking at number 3, part A, I already have a 1 as my constant in this location. So the eccentricity is just the coefficient on my trig function over here, which would be a 1, right? So e equals 1. Since e equals 1, this must be a parabola. For part B, on the other hand, I don't have a 1 in this location. I have a 3. So what I have to do is I have to factor that out, right? So I have to say, r equals 3 over 3 times 1 plus sine theta. And in this case, it just happens to work out that the 3's will cancel. So you get r equals 1 over 1 plus sine theta. And now this constant term is a 1. So I can tell that my eccentricity is going to be the coefficient here, which is just 1, right? So e equals 1. So again, this is a parabola. Let's do another one. So part C, I need for this constant term to be a 1. That means I need to factor out a 2. So I'm going to say r equals 12 over 2 times 1 minus 2 cosine theta. And the 2's will cancel. I get 6 over 1 minus 2 cosine theta. So the eccentricity in this one is 2. Alright? Since the eccentricity is 2, this conic section is going to be a hyperbola. Right? So this one's a hyperbola. Right? 2 is greater than 1, so we get a hyperbola. And let me give you one more, just to make sure that we've got it. Right? So here, this constant term is not 1. That means I need to factor out a 5. I'm left with 1 over 4/5 cosine theta, right? So hopefully that makes sense, right? Because when I distribute the 5 back in, I get 5 plus 4 cosine theta, right back where I started. Now this 5 here, I mean, you can tell now that the eccentricity is 4/5, so you don't need to really clean this up at all, but in case you're interested, right? So you could say this is 12/5 over 1 plus 4/5 cosine theta. That's important because if you're trying to figure out what P is, so P has the same interpretation as it did when we were talking about the planar definitions of the conic sections, right? So P is like your directrix if you're talking about a parabola, for example. So if you wanted to figure out what P is, then here you could say, well, I need to rewrite 12/5 as something times 4/5. Well, that would be 3 times 4/5, right? So this is really, I could say this is 4/5 times 3. And then that tells you your eccentricity is 4/5 and P is 3. But anyway, so I can, but the moral of this story though, I'm not going to get into all of that with the directrix and everything, but what I will say is that E is 4/5 and that's less than 1. So that tells you you've got an ellipse in this case. Alright? So once again, just knowing what kind of conic section you have will help you to graph these things, but I think you're still going to have to plot some points in order to get a good picture for what these things are going to look like. So, so I have 3 examples here. 3 examples. If I know myself, then I would guess that this is probably one example of each type of conic section. Okay. But let's see. So notice something else. Right? So just real quick, because this will make it easier to identify what kind of conic section we have. Notice that when I factor out this number, I basically just divide this number by that one. So another way to do the same thing is to just say, well, what's this divided by that? Right? 4 divided by 2 is 2, and that's your eccentricity. Right? Here you do 4 divided by 5. 4 divided by 5 is 4/5, and so that's your eccentricity. Right? 3 divided by 3 is 1, and so 1 is your eccentricity. Right? So you just do, if we call this A and B, you just do B divided by A. Right? B divided by A is your eccentricity. So that'll make things a little bit quicker. Like in this case, I can say B divided by A is 2/3. So my eccentricity is 2/3. That tells me that we have an ellipse, right? B divided by A is 2/3. So our eccentricity is 2/3. That means we have an ellipse. So I'm expecting to get an ellipse, but I have no idea, like, does it look like this? Does it look like this? I mean, where is the ellipse, right? So really, I just have to plot some points to get an idea of what this thing looks like. So I'm going to plug in some things for theta and see what I get for r. I think a good place to start would be to do like 0, pi over 2, pi. I'm leaving myself some space so I can come back and fill in some blanks if I need to. But I'm going to do 0, pi over 2, and maybe 3 pi over 2. And if that's not enough information, then I'll come back and do some more. But let's see what we get. I'm just going to do this in my calculator. So we have 5 over 3 plus 2 sine theta. So when theta is 0, this is 5/3. When theta is pi over 2, this is 1. When theta is pi, this is 5/3 again. All makes sense, right? And when theta is 3 pi over 2, this is 5. Okay, so let's plot those points and see if it's making any kind of sense at all. So 0, 5/3. 5/3 is, 1 2/3. So 0, 1 2/3. Then we have pi over 2, 1. And then we have pi 5/3 again, 1 2/3. And then we have 3 pi over 2, 5. 1, 2, 3, 4, 5. Okay, so I think it's an ellipse that's opening kind of like this, right? Remember that the pole here is one of your foci. So the other foci must be like right here, right? These must be your foci of your ellipse. So, so I think you get a picture that looks more or less like this. Now you can verify this, right, by plugging in some points. So in particular, it might be interesting to know what's happening down here at 5 pi over 4, for example. So at 5 pi over 4, what's going on? If we plug in 5 pi over 4, we get about 3.2. So at 5 pi over 4, we're at 1, 2, 3.2. Okay, so it's a little bit wider than what I made it. But yeah, that kind of confirms my suspicion. I guess we could say, what's happening over here at 7 pi over 4? 7 pi over 4. At 7 pi over 4. It should be the same value. Yeah, about 3.2. So 1, 2, 3.2. So again, I made it a little too skinny. Oh, was that right? 1, 2, 3.2. Yeah, so I made it a little bit too skinny, right? The ellipse. It should look something more like this. Okay, but that's the idea. Okay, so it looks something like that. You're welcome to graph this in Desmos, right, to verify that it's correct. But let's look at another one. So here we have r equals 6 over 2 plus 2 sine theta. The eccentricity is going to be 2 over 2, which is 1. That tells me that we've got a parabola, right? Yep. So we've got a parabola. Well, same deal. I'm going to plug in 0, pi over 2, pi. And then I'll plug in 3 pi over 2. And if I need to come back and fill in some blanks, I will. I have a feeling I am going to have to come back and fill in some blanks because this is a parabola, which is kind of weird because it never closes in on itself, right? Oh, and that makes sense because, check it out, right? You're going to get something undefined whenever theta is equal to 3 pi over 2, right? Because sine of 3 pi over 2 is negative 1. 2 times negative 1 is negative 2, right? And 2 minus 2 is 0. So I already know this one's going to be undefined. Well, what that tells me is that that must be the axis that this thing opens on. So I have a feeling it's a parabola that opens down, kind of like this. Okay? Because in other words, the graph can never close in around to get over to 3 pi over 2 because it's undefined there. So it's just going to keep growing and growing forever downwards in both directions. But let's see what we get. So we have 6 over 2 plus 2 sine theta. So when theta is 0, this is 3. When theta is pi over 2, this is 3 halves. When theta is pi, this is going to be 3 again. And when theta is 3 pi over 2, this is going to be undefined. Yep. So let's see what we've got. 0, 3, 1, 2, 3. Pi over 2, 3 halves, that's 1.5. And pi 3, 1, 2, 3. So this is a very wide parabola, and it's opening downwards, right? I think the picture we get is going to look something like that. Okay, so we're going to get something like that. We could verify this by plugging in a couple more points. Like, we might want to know, for example, what, 5 pi, what's happening at 5 pi over 4 and 7 pi over 4. If I plug in 5 pi over 4, seems like those are always the ones I'm plugging in to fill in the blanks, right? But if I plug in 5 pi over 4, that's about 10.2. Oh, that's off the charts, right? So 5 pi over 4, I'm at like 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I'm like way out here. So I guess it kind of it opens wider than the way that I drew it, right? Because it's going to come way out over here. Maybe another good thing to plug in would be like 11 pi over 6, right? Sorry, that was 5 pi over, but 7 pi over 4 is going to be the same, 10.2. 5 pi over 4 is also going to be like way out here somewhere. But yeah, if we plugged in like 11 pi over 6, then we get 6, right? So at 11 pi over 6, we just get 6, right? So that's 1, 2, 3, 4, 5, 6 at 11 pi over 6. All right, so you get kind of a better picture now. And then at pi over 4, we're all the way out at like 10.2. But this thing keeps going down forever, right? And it's never going to curve over and get to pi over 2. It's undefined there, right? So so this thing is ridiculously wide. Much wider than the way that I drew it originally. Okay? But hopefully that's more or less clear now, right? Your parabola is going to look something like that. Okay, so that's a parabola. And then one more. This has got to be a hyperbola, right? Let's verify. Right, so our eccentricity is going to be b over a. That's 7/3. That's greater than 1. So yes, this is a hyperbola. hyperbola. Oh, this one's going to be even trickier, I think. If it's a hyperbola, it's got to have two branches. So I have a feeling I'm going to be plugging in a lot of stuff here to try to figure out what's going on. Let's start with the standard ones, though. And see what we have going on. So this is going to be 20 divided by 3 minus 7 cosine theta. So when theta is 0, we get negative 5. When cosine is pi over 2, we get 20 thirds. 20 thirds. Well, 3 goes into 26 times with 2 left over, so this is 6 and 2 thirds. Okay, when theta is pi, we get 2. When theta is 3 pi over 2, we get 20 thirds again. Right? That's 6 and 2 thirds. Okay, interesting. So 0, negative 5. 1, 2, 3, 4, 5. Pi over 2, 6 and 2 thirds. 1, 2, 3, 4, 5, 6 and 2 thirds is like off the charts, right? Maybe something like that. Pi 2, 1, 2. Oh, yes. Okay. I think I see what's happening. And then we have 3 pi over 2, 6 and 2 thirds. 1, 2, 3, 4, 5, 6 and 2 thirds. So I think these 3 points are the right-hand branch of the hyperbola. And then I think this point represents the left-hand branch. Well, if that's true, then I'm either going to have to plug in 3 pi over 4 or maybe 7 pi over 4. I'm not sure which one will get me what I want, but let's try 3 pi over 4. If I plug in 3 pi over 4, is it's about 2.5. I don't think that's going to do it. 3 pi over 4, 1, 2.5. Yeah, I'm still on that first branch here. And cosine is the same in quadrants 2 and 3. So I know that I'm going to be at 2.5 again down here. 2.5 down here. So I'm still on this first branch. I wonder maybe if I plug in 7 pi over 4. Hopefully this is like a negative number that I get. Yeah, that's like negative 10.3. This is about negative 10.3. So at 7 pi over 4, I'm at negative 10.3. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.3, right? So at 7 pi over 4, I'd be like way up here somewhere, right? Way up here somewhere. Okay, which means probably at pi over 4, same thing happens, right? Pi over 4, and probably at, well, yeah, because cosine is the same in quadrants 1 and 4. So this is also going to be about negative 10.3. So at pi over 4, I'm at negative 10.3. So I'm also like way out here somewhere. But that kind of confirms my suspicion about this being the other branch, right? So I think this is one branch of my hyperbola. And then this is the other branch of my hyperbola. It's out here somewhere. Right? So that must be what this conic section looks like. So this one especially, I think, goes to show you why it's useful to know what kind of conic section you're looking at before you go to graph it. Because if you didn't know that this was a hyperbola, and you just plotted 0 pi over 2 pi and 3 pi over 2, and you got these 4 points, it's like, who knows what that looks like? It could be maybe a limacon with an inner loop. I mean, who knows, right? But if you know beforehand that it's a hyperbola, then you can say, oh, okay, it's a hyperbola, so I must be missing some information out here, and you can go through and try to find it so that you get a nice looking picture. So anyway, so there's that one. There's our hyperbola. That's all I'm going to say about graphing polar equations. So that'll do it for Chapter 5.